is the second most important one. ED202 is the most important, where you do a binary buffer overflow exploitation in Linux. So you see how it works, and then you want to see how it works on Windows. So here what we're going to do is run this vulnerable server in Windows, and if you have a server machine, you have to turn off data execution prevention. I think on the client machine it's off by default for what we're doing, and you turn off the firewall because we're listening on a funny port. All right, and then error reporting is optional, but you can turn that off too, just so you see a useful error message. All right, but the only thing is just to run this code. This is open source code specifically for this purpose called Vuln Server. So you download this thing and run it, and that's what you see. Well, we're seeing here the Zoom has somehow stopped. Let's see what happened over here. How do you get to the operating system where Zoom is? All right.
Maybe just reshare.
Yeah. Maybe when you went to full screen, the
Yep,
share went away
yep.
or something.
That's what
Yeah, you can leave it non-full screen, it'll be all right.
No, I think I got it.
Let's see. Yep, okay, good. Thank you. All right, so it's Windows machine. So what's happening is it's listening. Let me just stop it and show it to you again. Control C. Control C does not work. Oh, there, it does work. It's kind of slow. All right, so you download this thing, and it's here in your downloads folder. I imagine. Yep, there it is, Vuln Server. You unzip this thing and just double-click it to run it. And that will launch a command prompt. All right, maybe some kind of weird problem here. Double-click,
Should work.
right-click, open. All right, there we go. So now it's listening, waiting for client connections. And I can connect to it from my Linux machine. This is an SSH shell into my Linux machine, which I'm going to use as an attacker. And my Windows machine, let me open a, let's get its IP address here. If I go here and do CMD, there we go. And then IP config. I should be able to make the font bigger. Let me try that. There we are. Properties. Font bigger. Okay, so 192.168.0.215. Let's connect from Linux. Ping 192.168.0.215. Okay, I can ping reaches it, and so if you want to connect to that server, it's listening on port 9999. So netcat on Linux, Control E, 9999. All right, this is welcome to vulnerable server, enter help for help. And there are various methods here. It's intended to look sort of like an email server, but these are less meaningless words. These are functions that take parameters, and a whole bunch of them have vulnerabilities, all different kinds of vulnerabilities. But the one we're going to use is trun, which just takes a value, and trun has a simple buffer overflow, which is what we're going to start with. All other exploits are variations on this theme. So we can exit from here. I don't need to use the command line and interact it this way anymore now that I know it works. Now, all right, so that tests the server. So now we're going to fuzz the server. So we're going to use this program. So let me just do less of VS fuzz. All right, what this does, this opens a Python socket to the server on that port, and it asks you for the length, and it sends trun space period followed by that many capital A's, followed by a carriage return line feed. So it's just a lot of A's going in. This is what you often do for fuzzing, just a lot of data, trying to find a buffer overflow. So mode plus X, I'm going to make everything there, because there's a bunch of them here. So VS fuzz. Run it, so let's send 10 A's, and it returns with trun complete goodbye. So that means the server didn't crash or anything. In fact, let me see if I can get the Zoom window open here. This is good. So there's the Windows machine. Here's the Linux machine sending the attack, and you can see the two at once. So now I'm going to send more. Let's send 100. And again, everything's fine. Let's send 1,000. And again, everything's fine. Let's send 3,000. And now it gives a weird error, incomplete command, and I think it crashed. Let's get this out of here. Oh, I can't control it there. I got to control it here. There. Nope, still listening. All right. Anyway, I know if I send 9,000, it's going to crash. Yep. But they reconnected and listened again. But this unknown command stuff means it crashed. So let me go to my instructions. All right. So you try various ones. We would have seen this error message, but for some reason we're not seeing it. I'm not going to worry about it. Now we're going to use the debugger, just like we did with Linux, to see the structure of memory. So we're going to use immunity, and then run this thing, and then I'm going to send a crash with 2,000, which will do it. So let me show this Windows machine, and here, let's get I'm going to close the vulnerable server and run it inside immunity. Here's the immunity debugger, a free debugger you can use. The more modern stuff is x64 debug, and x32 debug is the modern replacement of these debuggers, which are all pretty much based on Ollie debug. But anyway, they're all fine. There's immunity. Now I can do file open and go find that vulnerable server, which is in the downloads folder. And vuln server, vuln server. Okay. Now debuggers always do the same thing. They load the program and it's not running. Now I also want to fix it so you can see things by making the appearance different. So appearance, font all, OEM fixed font, that helps. And now I can make it better with options, appearance, and modify the OEM fixed font to be something bigger. OEM fixed font, change. And I want to make it Lucida, bold, 18 will probably do. There. Now we can see what's going on here better. And you got to get used to this layout. And of course, the first thing is you have baffling too much information, but you get used to it. The first thing is look down in the bottom right corner. This is a fundamental rule for all these complicated tools. The main screen is full of the complicated details that only experts can understand. All the stuff for beginners is shoved over in the corner because the experts don't want to see it. So when you're a beginner, start on the corner. The bottom, the right in the corner is where the good stuff is. Right down here it tells you the program is paused. Debuggers always do this. They load the program in memory and then they stop because presumably that was what you wanted it for, to examine memory and put breakpoints in and stuff. So you can't attack it yet, it's not running. That's one fact. Then there's the 4 panes. This is the assembly code, showing the raw assembly code of the program. Notice it is about 400,000 is the address. Windows programs always think they're running at 400,000. That's a virtual address. That's where they like to load. And the first 1,000 in hex bytes are used for metadata, and the code actually starts at 401,000. That's where the executable code is, and that's where we are, somewhere in that area. So here's the code that's going to run. This is the raw hex, and here's the assembly code. Then over here are the registers, same thing we saw in GDB. Here's ESP and EBP, that's the stack frame. Here's the instruction pointer, and so this is the usual stuff. Down here is just a hex dump area where you can dump anything you need to in hex just to examine it. And on the right is the stack. This is the stack, and it shows you that's why these addresses go up 4 at a time, because this is a 32-bit code, and so addresses are 32 bits long. This is just a series of addresses in the stack. This is the returner to the kernel, return to the NTDIL, and so on. When you launch a program, the NTDIL and the kernel are Windows processes that are used to launch the code. And if you call the subroutine in your code, you'd have a deeper stack frame with more pointers returning to parts of the code here. So that's what's happening. Now we're going to run this thing. Now it's running. And now I'm going to attack it from my Linux machine here with this fuzzer, and I'm going to send 2,000 bytes. And when I do, it's going to crash. At the bottom it says thread terminated, exit code 0. So it's, and let me see if I can view the log over here. Window log. All right, now I got to fix the stupid invisible font. Font OEM fix. There we go. And so thread terminated. All right, so I expected to see a crash, and for some reason I didn't see the crash I normally see there. I should have seen an access violation when writing to 414141. Let's see if the next one works. If not, I may be in trouble here.
Just throw 9,000 on it, I think.
What's that?
Just throw 9,000 at it.
Oh yeah, I couldn't throw 9,000. Yeah, this was the one. What I wanted to show you is there are two different crashes. Now I don't know why this one didn't give us the expected error message. That's a little disturbing. It should have shown trying to write. See, the point is this one tries to write to some of those A's that went in there, and the other one tries to execute those A's, so it's the easier one to exploit. So this is what happens when you send it 3,000. Let's see if that works. Otherwise, there may be a problem at my demo, which seems to be happening a lot today. But anyway, go to the CPU, and whenever you have a crash, I gotta make this thing. All right, you go debug, restart, to get this thing to load again, and then I run it again, and now I can attack it again with 3,000, and let's see if it crashes. And it does not crash, so my demo may be host. I don't understand. What's that?
Try restarting the server.
Restarting what?
Restarting the server and doing it again.
The Windows server completely. Okay.
Yeah.
I'm confused how this is possible. Let's see if I can figure out what is going on here. All right, let's try restarting the server. That's the general solution for everything in the world of Windows, of course. This is a 64-bit Windows 10, right? And it has no excuse to be like this. And I'm sending the data. I don't think anything can be wrong with my code here.
I had this problem before when I taught the class.
Did you?
Yeah, and it just, I don't know why. But
The
it
restart
worked.
fixed it?
So,
Oh, good.
Fingers crossed it'll work this
Oh,
time.
good. I'm glad to hear it. I never had this problem, but this is VirtualBox. I often have trouble with VirtualBox. But the data is going in. That's why the next thing is run Wireshark at the other end and see if the A's are actually getting in.
Yeah.
Remember, I taught many times, every time you have networking problems, the answer is always run Wireshark at both ends. Find out what you're sending and what's actually getting in. It is possible that it's usually something wrong with the networking in virtual machines, especially in VirtualBox.
Have you tested the connection again? Just to make sure it's the same. Oh, yeah, you did. You brought
Yeah,
up the
I did a
ping
ping and I did a
everything,
netcat, yeah. But when I did the fuzzing earlier, it didn't have the expected result. Yeah, go ahead and log in. Let's see. We'll see what happens here. All right, good. All right, there it's up. Let's try immunity again. And how do we make it bigger?
It's not
Why is
full
immunity not?
screening.
Oh, okay. There's immunity. That's a start. Okay. Can we?
Let me
There's no,
fix it.
there's no way to make it bigger?
Yeah, there is.
Okay.
Hold on.
That would be nice. But, F11 maybe?
Hold on just one sec. I got to leave full screen to do it, though. Is the only problem.
All right. Okay, thank you. All right, so let's try it again. File. Oh, just garbage. Okay, file.
Don't forget to restart the server.
Yep, this thing. Yep. And then gotta fix the stupid appearance. Fonts all. Oh, neat. Didn't remember my settings. Options, appearance, fonts. Wait a minute, I gotta have something weird happen. Change. The OEM fixed font. Change. Lucida. Bold. 18. Okay, now we can see what's going on. Now I run the server, and it's running. Now I'm going to try the fuzzing. So that is here. That's nano. I got to run it, which is there, and 2000. And it just does this single thread terminating again. It's like multi-threaded somehow, which I'm afraid means I'm toast. Well, I've never seen this before, and I
have it
don't.
working with 2000 on my machine.
Yeah. So it's something wrong with this Windows machine. That's a bizarre thing. All right. Well, I'm going to have to just describe it. I can't do it live because somehow this Windows machine doesn't work. It's turned it into a multi-threaded application, so it doesn't crash. It just terminates one thread, which is mind-boggling.
Yeah.
It's not a multi-threaded code. But anyway, some bizarre thing has happened there. You're on the. Maybe you can attack yours. Are you on the DEF CON network?
Yes.
He can
Well,
hear
here.
your Zoom.
Yeah, let's try that. Good. So let's see. Let me.
Yeah.
I'll just stop the share.
I'm not sure.
If you join my Zoom, you can share your desktop.
Not bridged, so
If you're not bridged, you'd have to be bridged. Can you switch it to bridged?
I can try.
Are you VirtualBox or VMware?
VMware.
Oh, good. If you're VMware, it'll probably work. This is awesome. I appreciate the help. Then I should be able to just change the address here. We'll see what address you come up with. And I should be on a DEF CON network, right? Let me get on there. We will see.
The WPA3 network.
A WPA3. All right. That means I think I have to download more stuff. I just got on the BA2 because I wasn't interested in understanding this stuff. No, that's right. I have to be on something. Right, no internet. Oh, here we are. All right, so DEF CON, I actually downloaded these three things, but I couldn't understand them. All right, so there's three things you have to download and they didn't.
Yeah, I'm not sure I can get through it. Not getting the IP back to my VM.
Yeah, maybe
I
the
bridged it. I don't think they allow.
They don't allow. VMware does, but
Yeah, I don't know. I'm just getting an auto configuration IP address.
yeah, that's what happened to him. He couldn't get any DHCP.
No.
Okay, yeah, maybe the DEF CON network is what prevents that, because you have to authenticate inside the VM. That's probably it. Can you join your hotspot?
Yeah.
Okay, let's try to you to join her hotspot, because her hotspot gives us a naked network without all this hogwash. That's what happened with the DEF CON. You'd have to import the certificate into there.
Yep.
Yeah, okay. That makes sense, actually. All right, good. So I'm back in here, and that's ping Google. All right, I'm on something, and IPA. Okay, I'm on 192.168.121, which I guess is your hotspot. Your hotspot is 0, isn't it? Let me see what's going on here. ifconfig en0. Your hotspot is 192.168.0. Okay, so I think I need to do a DH client reset on my Debian to get it on the same network. So that's going to be sudo DH client -v, and that will lose connection, of course. What? There we go. Good. And that should lose connection when it gets a new address. So I should be able to go to my virtual machine here and find out what my address is. Okay, IPA. It's still 121. Perhaps this thing is on NAT. It is. Bridged, okay. I don't understand how I was reaching a machine before then. I guess I don't need to be on bridge because for the attacker, just for the defender. Okay, connection established, good. IPA, now I'm 192.168.0.254. All right, let me get in here. All right, it's not letting me terminate things in the terminal. All right, SSH Debian at 192.168.0.254. Am I supposed to believe that? Let's try that. Apparently it's true. All right. All right, so I'm in. And what's your machine's address?
It's 116.
192.168. 116?
Yeah, that's 0.1.
0. Oh, 116. I'm with you.
Yeah.
All right. Is your firewall off?
It should be, yeah.
Well, I can't reach you.
Just a second. Let me double check.
Yep.
The only thing that proves it positive.
Now you can join my Zoom and share your desktop. That's another thing to do. Let's see if I can greet you.
I have my host firewall on, just.
Your host's firewall. Oh, yes.
So that should probably go off there, yeah.
Okay. Still no pings.
Thank you.
Okay, farewell.
I have pings to 254.
Your ping is 254?
Oh, I can ping 254.
You can ping 254. Okay, let's see.
All
Right, why don't you run that server? Let me see if I can connect. I'll netcat to 192.168.0.116 on 99.99.
Yeah,
That's what I need.
Excellent, yeah.
Nope.
All right.
You must have a firewall or something.
Checking more firewalls then.
Yep.
Yeah, it may have been switched on by changing networks. Yeah.
Ah, good. There's always something.
Yeah, it's all off. So weird.
Let me try from my host's Mac. See if that does any better. Nope. Nope, can't get any traffic through to you. This thing doesn't. Oh well. Well.
I'm working on it. It doesn't
All right.
what now?
Nope, doesn't work. I can't get through to him at all for some unknown reason. Well, I'm going to talk about what would happen if we get the demo work, which is clear that it's not going to work. Some kind of networking problem, and whatever makes the Windows machine turn into multi-threading bizarrely, that's a screwy one. I can't even understand how that's possible. But anyway, all right. The point is you then have the 2,000 characters in the attack, it crashes on a write operation, writing to some of those A's. And you can take over a machine with the write operation, but it's not as straightforward. What's easier is an execute operation, and with 3,000, it takes some of those A's and tries to execute that code. So now you just have to find which of the A's it's trying to execute. So you do that by making a non-repeating pattern of characters, and there's various ways to do it. I chose to just write a Python script that will have 000A, 001A, 002A, and so on, up to 499A, so that's 2,000 characters, and you put in 1,000 and then that junk, and then you can send that non-repeating pattern to the server and find out now it has an execution violation when executing this, which is 1A25, reading it backwards. And the 1A25 is here, 1A25, and so you can figure out how many bytes in that is. And it does depend a little bit on your version of Windows. It moves a little. And so then you can make a attack code that targets the server precisely. 2006 gets you to the right area. BCDE is going to go in the instruction pointer. And then you fill it into a total length of 3,000, which is really important, like I mentioned before, because if it was shorter like 2,000, you would not be hitting the same flaw. And so now you check to see if the BCDE goes in, restarting it in Debugger, and you'll see it crashing BCDE. 40, that's what you got to see. Then you have to control the instruction pointer. Now you can put anything you want in there. Now you can examine the memory at ESP. Right here, you can just go to the ESP and follow in dump at the point of the crash. And when you do that, you will see here a bunch of F's. And maybe the exploit I used was a bunch of A's, then BCDE to hit the EIP, and then F's thereafter. And if you scroll back just a little, you will see this is the very first F. So when it crashed, the very next byte after the EIP is where the stack pointer is pointing. Now, Windows has address space layout randomization turned on, and you cannot turn it off. So you can't just find an address and jump to it because everything is randomly moving. What you need to do is find a jump ESP and execute that, and then it will go to here, and that'll be this F here, which is under my control. And you can do that because we turned off data execution prevention, which would turn off execution on the stack. So that to make it easy, we can put code here and execute it. if we can find a jump ESP. But if address space layout randomization was really working, I wouldn't be able to find any code to use. But the fact is, Windows defenses aren't thorough. They don't apply to everything, and that's what this thing called Mona is for. But then there's the issue of bad characters. Remember, some characters will break the string, like null bytes and tabs and carriage returns and so on. So you have to check for bad characters by just making something that will send 256 bytes, every possible byte, to the server, and then you see if it gets there. And if you just send the bytes from 0 through 256 and look in the RAM, you will find that none of them got there because the 0 terminated it. So you have to quit sending 0 and send it again, where you go from 1 to 256, and then when you look at the RAM on the server, you'll find there it is, 1, 2, 3, 11, 12, 13, right down to F1, down to FF. So every character is good except null bytes. So that's the first thing you have to do, is make sure you know what characters you have to avoid. Now I need to find a jump ESP. You found it?
Oh, sorry.
Okay, never mind. Anyway, and so for this you need Mona. Mona is a plug-in to Immunity, and it diagnoses Windows modules and what defenses they have. Because if you run Mona modules down here, it will tell you all the modules that are currently running, which are like these Windows system DILs, and then it tells you which defenses are turned on. The most important one for us being ASLR, and you can see there are some modules that do not have ASLR. And this is for a very simple reason. These are the modules in this program. It is Vuln Server itself and the DIL that came with it, essentialfunctions.dil, because it's legacy code. It was compiled long ago before ASLR, and ASLR is turned off for it. And we did this in Linux with the 64 by turning in the -no-pi switch. You can execute code that is not prepared to be randomized in memory, and it can't randomize in memory. In order for it to randomize, it has to have a relocation section, which is used to fix the static addresses. And if you compile it without that, it can't randomize it, and that was the case here. Now, the Vuln server itself, as I mentioned, loads at 400,000 in RAM. And therefore, it's no good because every address will start with a null byte. But the DIL loaded somewhere else. The DIL loaded at 6250 followed by 4 zeros. So the addresses in the DIL do not contain null bytes, most of them. And so if I can find a jump ESP in the DIL, it will not randomize. And that's called the trampoline attack. I go to the code I need, and it bounces back into the place I need to go, which I can't find. It does a jump ESP, and I don't know what ESP is, but I don't care because I control the data at ESP. And that's what we're going to do. So that's the game. You find that one. Now you use Metasploit to make your shell code. Metasploit will make shell code with, first you can make dummy shell code. First you got to make sure it's going to work. So you can make a dummy exploit that goes like this. You put in the instruction, you have the 2006 bytes to get where you need to be. Then you put in one of the addresses Mona found you. Here Mona found the addresses. There are 9 places where there's a jump ESP in the DIL. And all of them are perfectly fine. These are jump ESP instructions. It's a fairly common instruction. So the first one is fine, 6250 11AF. So you put that in here, 6250 11AF. Now you make a dummy exploit. You make a NOP sled, 16 bytes of 90. 90 is NOP that does nothing. So just do NOP, 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 NOP. Then you make a break. You make a break here, CC, that will break and return to the debugger. That's the kind of break we were putting in with the break instruction in the GDB. And then you just have enough padding to get a total of 306. So the attack is now the prefix, the instruction pointer, the NOP sled, the break, and the padding. This is it's not real shellcode, but I'll know if it runs because the NOPs have to run and the break has to run. And if there was data execution prevention, none of it would run because they're not allowed to run any data on the stack. So this is a test to see if DEP or anything else is going to stop you. So you run this, and you can see in the debugger that it stops at an int3, which is the break. So it did the NOPs and the break. And you can tell by scrolling back, here's the Fs, here's the break, here's the NOPs. It executed the 16 NOPs and the break, so that proves I do have control of the pointer, the trampoline worked, and I can execute code that I inject here. So all I need is good code to put there. And so you just make that with Metasploit. You go to Metasploit and you can use MSF Venom. This will make a reverse shell calling up your command and control server. you have to tell it to skip null bytes. That's what this does. A bad character is null bytes. And you give it a port. I'm going to listen on 443, so my traffic will look like HTTPS. And it's going to be Python code. And it creates a whole bunch of Python code for you. You copy and paste that into your source code. And this is what it looks like now. You have the 2006 to get to the vulnerable spot. You have the instruction pointer that points to a jump ESP. You have 16 bytes of NOP sled, which, by the way, you always have to have before Metasploit shellcode. This is one of the things that cost me weeks of suffering. Metasploit shellcode needs that area to expand. They don't tell you this anywhere I could find. My little shellcode kept crashing, and this is one of the many reasons that causes it. You have to have a NOP sled before the shellcode. Then you have the shellcode, and then you just pad it with enough Fs to make the length right. And now you can run a listener and mail a reverse shell. When you run it, it will give you a reverse shell up here. This is your Linux machine attacking. So you attack it here with one window into your Linux machine, and you receive the response here, and you get the meterpreter shell, and you're in. So that's all the steps for a Windows buffer overflow. And that's all I can do. I can't demonstrate live because of our technical problems, but such is life. There's always something. So let me stop this recording.